Hi, this is Jerry Pinter. Welcome to Chapter 2, Part 5, Block Diagram, Representation, and Discrete-time LTI Systems Described by Linear Difference Equations. We're going to start by looking at block diagram representations. So a block diagram representation of a system is, there's a couple examples shown here. This is a block diagram for a continuous time system, and basically what this does is it takes the equation for the system, which is a differential equation, and it replaces all of the mathematical operators basically with symbols here. And the same, we're going to do the same for a discrete time linear difference equation. We're going to likewise come up with a block diagram representation for that system as well. So a block diagram is basically a pictorial diagram of a system's equation. It's a signal flow chart, which is represented by the arrows in the block diagram. The arrows represent, you can see X coming in over here, and it goes into an adder here, and X also goes into, this is just a multiplier, it multiplies by 3, and then it takes the derivative, d dt is a time derivative, and the output of that goes up in here in the adder and so forth. So we can kind of use the diagram to see how the signals flow throughout the system. And notice that oftentimes the output, which is over here, that signal will be sent back into the system as sort of a feedback type of loop here. Basically the block diagram has simple interconnections between elemental mathematical operations. For example, add, multiply, differentiate, integrate, delay, etc. So we see all that, in this diagram. This is an addition. When we have a block just with a number in it, that's usually just represents a multiplication. And then this, of course, is a derivative. And we'll learn about this one here. This is a delay element, which we're going to encounter later on in the lecture today. These block diagrams are also useful for simulating system behavior in computers, and very useful for implementing and building a system with hardware, because we can kind of see how the basic elements or hardware pieces of the system are interconnected with the arrows that represent the signal flow. So let's start and see how we can construct a block diagram representation of a system based on its linear differential equation. So this is going to be a continuous time system. So let's go right through an example here. Suppose we have a system that's described by the following differential equation. 5 dy dt plus y is equal to 3 dx dt plus x. So our goal is to represent this equation using a block diagram that consists of adders, multipliers, and differentiators. So let's start by writing the equation with y on the left side. So we're going to take this, and basically we're just going to solve it for y. This is going to make it in a more convenient form to write the block diagram. So here's our y all by itself on the left, and we've got y is equal to minus 5 dy dt plus 3 dx dt plus x. So we can see right away in this form that our output of the system, y, all right, is equal to these three terms all added up. All right, so remember, a typical system here, our convention, the notation is x is the input coming in from the left into the system, and y is the output coming out of the system. So what I know here is, here's my x over here, my input, and here's my y over here, my output. I know that the output right here has, there is the result of these three things added together. So I'm going to put my summation symbol in the middle here. Now we have to figure out what goes into this addition operation. Well, there are these three things right here. So let's do it in reverse order because it's a little easier. The first thing that goes in, we see, is an x. Well, that's simple. We just take our input here and we draw an arrow, a signal flow, going right into the addition. The next thing we see is this term here. It's 3 times the derivative of x, 3 times dx dt. So I'm going to take my x, I'm going to multiply it by 3, and then I'm going to send that, which is 3x, through a differentiator. All right, that's this box that's labeled d dt. That means we take the time derivative of whatever goes into that box. And then the output of that we're going to put into the adder, because remember, it's added to these other terms here. And then finally, the last term that we're going to deal with here is this minus 5 times dy dt. Well, notice we're dealing with y, not x. So I have to take the output here, the y. I'm going to multiply it by 5 with this box, and then I'm going to send that through another differentiator, another subsystem that's labeled d dt. And the output of that will also go into the adder. So you can see now we're adding up three things. We're adding the x term, we're adding the second term right here, and we're adding this, first term in the equation over here, and all of that comes out of the adder to form our output. So this is the block diagram. So this is basically how we build a block diagram from the equation using these steps. The next thing we can do here is simplify our block diagram by minimizing hardware. And this is obviously a good thing to do. It not only is more efficient and economical to reduce hardware, but it also makes the diagram simpler. It cleans it up basically. So let's if we notice our equation here again, the one that we solve for y, notice there's two derivatives here. There's two time derivatives. So what we can do here is kind of factor out a time derivative here and put whatever we're going to take the derivative of in parentheses here. So there's a minus 5y, that's the minus 5 here, and then there's a 3x that's going to be differentiated. And so by putting those in here, we're sort of doing the opposite of distributing. This kind of cleans it up because now we can just use a single differentiator here. In other words, we can take 3x, which is here's x times 3, and we can take minus 5y, so here's y times minus 5, and we can just add them together. There's a summer there, or an adder, and the output of that goes through a single differentiator, and then the output of that is added to x. You can see here's the x over here. So this is a little bit improvement. We've got one less differentiator. We have added an adder to it, but probably this is a little bit of a simpler diagram to understand and try to analyze. The next thing we're going to do is get rid of these differentiators, and the reason for this is that differentiators are not practical to implement into systems because they're very sensitive to noise. So for example, let's say our input signal here, x of t, is going to go into a differentiator, and the purpose of this is obviously just to take the derivative of x, so the output here is dx dt. So imagine x, instead of being a nice smooth signal like shown here, imagine it has some noise, and that noise is represented by these spikes in the signal. Well, remember what a derivative does. It takes the slope. So you can see these noise spikes have very large slope. All right, it's almost infinite in some cases. The spikes kind of are just vertical lines here in the signal. So what happens is our output has these horrible distorted peaks and valleys in it because of the noise here. Each one of these has a large slope, so we get a very large swing in the output. So this is obviously not desirable. So integrators, it turns out, are much more immune to noise, because remember what an integration does is it finds the area under the curve. So the noise spikes, even though they may be rather tall, like is shown here, they're very narrow. They're typically tiny fractions of a second, this type of noise. So when we take the integral of these noise spikes, it's a very minimal effect. So there would just be, maybe you'd see a slight little bump in the signal here due to the noise, but this is obviously a huge improvement over something like this shown up here. So our strategy is we want to replace differentiators like up here with integrators down here. And notice an integrator is a little box, and it's just got an integral symbol in it. Okay, so that tells us it's going to integrate. All right, so how do we do this? How do we replace these guys up here with these nice integrators down here? Well, the way we do it is we convert the differential equation to an integral equation by simply integrating. So remember our form here, y equals time derivative ddt of negative 5y plus 3x in parentheses, all plus x, right? This was from the last slide. Well, we want to get rid of this derivative here. So the way to do this is you can multiply through by this dt on the bottom. So multiply all terms. So we have y dt equals d of minus 5y plus 3x plus x dt. And then we can integrate every term. So just integrate the whole equation. So on the left here, we have the integral of y dt. Now, when we integrate a total differential like this, all we do is basically get rid of the differential. So this second, this term right in here, just the integral here basically cancels the differential term here. So we end up with just what's inside the parentheses, minus 5y plus 3x. In other words, we've gotten rid of our derivative. And then on the right here, we have the integral of x dt. So this is not necessarily a simpler equation because now instead of a differential equation, it's an integral equation. However, we have achieved our goal. We've eliminated the derivatives and we've replaced them with integrals. So what we can do now is build this thing. And again, we see that y, the output, is the sum of two terms, this term here and this term here. So let's take care of the easy one first, this first term. We've got minus 3/5 times x. So here's x. I'm going to multiply it by minus 3/5, and I'm going to add it, put it in an adder right here. The other term that I need to add it to is a little more complicated. I have to take, notice I'm going to take x minus y and integrate it. So here's my x. Let's add that to negative y. All right, so here's y with a minus 1. So this arrow coming out here is x minus y. I'm going to multiply it by 1/5. That's the 1/5 in front here. All right, and then finally I'm going to integrate the whole thing. So that's the integral here. Notice this box here, this 1/5, it could come after the integral or before. It doesn't really matter where you put it. But here is our final result. And so this is our block diagram of this same system, but it includes an integrator instead of a differentiator. So this would be a much more practical system to actually implement or build, because this guy right here is not very sensitive to any noise that's coming into the system through the input here. Oftentimes we need to work backwards, and that is we have to find a differential equation from a block diagram that we're given. So let's just work through an example here. Let's say we're given this block diagram. All right, now you're not given any of the red notes here. That's how we're gonna analyze this thing. But you're given just the block diagram, all the boxes and the black arrows and so forth. So the way to figure out what the differential equation is for the system, it's actually not that difficult as long as you do it correctly. The trick is to label every arrow starting with x, and also you can start here at y. And label these arrows, follow the directions of the arrows until you get all the way back around to y. All right, so let's just go through this one to see how to do this. So what I'm going to do here is I'm going to start over here with x. So notice x goes to an arrow here, which is obviously just x. Also, x goes down here, so I'm going to label this arrow x. Okay, now this one down here, this x goes into a multiplication of 3. So what comes out of here, I'm going to label this arrow 3x. Likewise, over here, I have y coming down. So I'm going to label this y. Y is multiplied by minus 5, so this is minus 5y. Now I can take these two signals, 3x and negative 5y, and add them together to get this arrow right here. This signal is 3x minus 5y. And then, of course, this signal here, or not signal, this is a differentiator. So this is going to take the derivative of whatever goes into it. So this is the time derivative, ddt, of 3x minus 5y. That, in turn, gets added to x right here. So what comes out of the adder, this signal along the top here, is this x plus this signal down here, ddt of 3x minus 5y. And notice that this signal up here, this branch, goes right to the output, so therefore it's equal to y. So therefore I can write equals y. So this up here now is our differential equation for the system. All right, and in fact, we can go a little further now. I can distribute the derivative inside the parentheses, and I get this equation here, and I can place all of my y's on the left side, which is customary, and all my x's on the right side, and here is our final differential equation for this system. So there, it's just as easy to work backwards, from the diagram to construct an equation, or we can go the other way. If we're given an equation, we can construct a diagram. So at this point in the lecture, we normally break out into our groups in the classroom and do an activity. So this is the activity here. You're given this block diagram right here, and you're asked to do 7 different questions here based just on this block diagram. And so what I'd like you to do is, for practice, you can pause this video and get some scratch paper out and see if you can figure out the answers to all of these 7 questions here, and then we'll go over them when you're done. Okay, so the first part of this activity is to find the system's differential equation, and notice I gave you the hint here, label every arrow in the diagram. So from this diagram here, what I'm going to do is I'm going to label, I have x coming in, there's a -1, so this is minus x here. I have y over here, it goes through a differentiator, so this is dy dt coming out, it's multiplied by 3, so this signal here is 3 dy dt, and that gets added to negative x. So what comes out of the adder here is 3 dy dt minus x, and that must be equal to y. So I've got y is equal to minus x plus 3 dy dt. All right, that's the final step. This output here is the same as this, what I've written right here. And I can rewrite this. I can put, as is customary, I can put all the y's on the left side. 3 dy dt minus y is equal to x. And so there is our differential equation for the system. Question 2 was find the homogeneous solution. Remember, this is the system output for no input, or equivalently a 0 input. So our homogeneous equation, remember, we just make the right side 0. This is something that we discussed in part 4 of this chapter's lecture. What we have to do is write the characteristic equation. Remember, we can do this by inspection. A first derivative just gives us an s. So I have 3s minus, y by itself just gives me the 1, equals 0. I can solve for that. S is equal to 1/3. So my homogeneous solution, y sub h, is equal to some constant c, which we don't know yet, times e to the t over 3. Remember that we have st up here, where s is 1/3. So that's how I got that. All right, the next question, find the particular solution for the input signal x of t equals e to the minus t ut. So what I have to do here is I have to go back to the previous video, part 4, chapter 2, part 4, and we figured out how to solve, this is an inhomogeneous or non-homogeneous differential equation because the right side has this on it. And so I need to look on that chart and find the form of the particular solution. So this is obviously an exponential function, and it turns out that the particular solution will have the same form. So it'll have some constant a times e to the minus t, because that's what we see here, e to the minus t. And also I'm going to put this step function on it because I have that here, meaning this signal only exists for t greater than 0. So the next thing to do is to take this solution here for y, and substitute it back into the differential equation in step 1. So when you do that, you're going to get minus 3a e to the minus t minus a e to the minus t equals e to the minus t. And this is valid for t greater than 0. Notice I didn't put any of the step functions u of t in there because we're going to solve this for t greater than 0. All right, so how did I get this again? I simply put this solution back into the differential equation. Now obviously I had to take the derivative of the first term because there was that derivative there. But that's where this comes from. Now we can solve this for a pretty easily. Notice all the terms have e to the minus t, so we cancel those and we get minus 3a minus a equals 1. In other words, a is equal to negative 1/4, just doing a little algebra there. And I can plug that back into my particular solution here. So our particular solution, y sub p, is equal to minus 1/4 times e to the minus t times that step function, u of t. So the next step, question 4, find the total solution assuming the system is initially at rest. So remember, our total system is just the sum of the homogeneous solution, which was found up here, and the particular solution, which was found right here. So here I put those two terms in there. And since the system we're told is initially at rest, we've got an initial condition. When when t is equal to 0, we have y of 0 equals 0. That's our initial condition. And when we set t equal to 0 over here, these exponential terms just go to 1. So I have c minus 1/4. So this can easily be solved for c. c is equal to 1/4. So here is my total solution. Our output of our system is equal to 1/4 e to the t over 3 minus 1/4 e to the minus t times the step function. Part 5, modify your total solution assuming the system is causal. Well, what this means is that if the system is causal, then the output has to be 0 for t less than 0, since the input is 0 for t less than 0. So the output y of t can be fixed, basically, by affixing a step function to it. So all I've done here is just added this step function u of t to both of these terms here. Before it was just on the one term. Now it's on both. So this basically means this output goes to 0 for negative time, okay, because of this step function here. The other thing you can notice is I've factored out the 1/4 just to clean up a little bit. Okay, question number 6. Is the system stable? Justify your answer. Well, we can look at these two terms here and decide what they do as t gets large. The second term is well behaved because it's a decaying exponential function. When t goes large, this part goes to 0, so that's fine. But this term here sort of violates our stability criteria because for large t, this term is going to blow up. So this system is unstable. Okay, the last step here was to redesign the system without using differentiators by using a single integrator along with any other necessary components. So again, the trick here is to take our differential equation that we started with and get rid of this derivative. And the way we do this is simply by integrating. So I'm going to multiply through by this dt on the bottom. So I end up with 3 dy minus y dt equals x dt. And over here, let's see, what I'm going to move this term over to the right and factor out the dt. So I get 3 dy equals x plus y dt. And now I'm going to integrate both sides of this equation. So I'm going to stick the integral sign here on the left, and on the right, I'm just going to take the integral of that whole term there. And finally, the integral of dy is obviously just y. You can see I also divided by 3 to get rid of the 3 in front, so there it becomes 1/3. And on the right side here, I have the integral of x plus y times dt. So the way I can do this now is notice my output is I have to take x plus y and integrate it. So how do I do this? Well, here's x, so I've got that going into an adder. Here's y, I'm going to bring that around and add y to x. So this is x plus y coming out right here. So that's my term in here, and then I'm going to multiply it by 1/3, which is out here, and then integrate the whole thing. All right, this is the integral that takes care of that, and that gives me my output here, y. So this thing, boils down to a relatively simple block diagram representation with we've got an adder, we've got a multiplier here, and we've got an integrator. Okay, so for this last part of the video, or last half of the video, we're going to switch gears and we're going to turn to discrete time systems. And discrete time systems are described by linear difference equations. So, the key word here is it's not a differential equation, which is continuous time. In discrete time, we call it a linear difference equation. So we're going to learn how to represent a system, a discrete time system, using a linear difference equation, and we're going to learn how to solve linear difference equations. Okay, so as I just mentioned, analogous to continuous time systems, many discrete time systems can be described by a linear difference equation. So here's an example of one right here. Y of n plus 2y of n minus 1 minus 8y of n minus 2 equals x of n. And x of n is given as the sequence here, 3 times 1/2 to the n. All right, so notice what we've got here. This is called a difference equation because we have y by itself, and then we have these delayed versions of y. This is y of n minus 1. This one here is y of n minus 2, and then those are in turn multiplied by coefficients, by linear coefficients, which makes this a linear difference equation. So notice, we don't have derivatives. This is not a differential equation. There's no calculus here. These are just delayed versions of the various signals, and this makes up the so-called difference equation. So the good news here is that the method for solving linear difference equations is very similar to the method that we just used in the last video to solve linear differential equations. So we're going to start by finding the homogeneous solution when x of n, the input, is equal to 0. So the trick to do this, there's two tricks. First of all, we're going to set the right side of our difference equation to 0. And the next trick is to realize, and again, I'm stating this without proof, is that the solutions to these linear difference equations are always these exponential functions, some number r raised to n. N is our time, our discrete time variable. So we're going to let y of n, the solution here, be equal to r to the n. All right, and let's see what happens when we do that. So we're going to plug this in. Wherever we see y of n, we plug in r of n. So y of n here becomes r of n. This is 2 times y of n minus 1. So that's 2 times r of raised to the n minus 1. And then here we have minus 8. Y of n minus 2 becomes minus 8 r raised to the n minus 2. And that all, of course, is equal to 0 because we're looking for the homogeneous solution. Our goal now is to basically solve this for r. All right, so at first glance, it's not very obvious how to do this, but what we can do here, there's a couple tricks, is always look for the lowest power exponent, all right, which is the n minus 2, and we're going to, this equation here has to be valid for all values of n. So let's choose n equal 2 to make this sort of clean itself up and make more sense. All right, so if we let n equal 2, this first term becomes r squared. This term becomes 2r by itself. And then the last term, this is minus 8r to the 0, which is just 1. So we end up with minus 8, and that's equal to 0. So this equation inside the red box here is the characteristic equation for this system's linear difference equation. And we can solve for r by all the, any of the usual methods. And this one is nice because we can factor it. R plus 4 times r minus 2 equals 0. So our two roots, r1 is equal to -4, and r2 is equal to 2 from that factor. So our homogeneous solution is, we're going to call it C1 times r1 to the n, remember r1 is -4, plus C2 times r2 to the n, where r2 is 2. So plugging in those values, here is our homogeneous solution. Our homogeneous solution, y sub h, is equal to C1 times -4 to the n plus C2 times 2 to the n. The next step is to find the particular solution, just like we did for solving differential equations. So our particular solution, y sub p, we have to find the correct form for the input. Now this is what we were given on the previous slide. The input of the system is 3 times 1/2 to the n. So here's our table, just like we had, for differential equations. There's a table here for different forms of input over here on the left, and here is the particular solution form over here on the right. So this, if we look at x of n, this is a form of some number raised to the n, and you can see that's this form right here. We have a constant out in front. We have, our constant is actually 3. And then we have b is 1/2 raised to the n. So our particular solution is going to be another constant, just a different constant, we'll call it c, times the same base number, which is 1/2 in our case, raised to the n. So from this table, we simply read off y sub p is equal to c times 1/2 to the n. The next step is to plug this particular solution back into the difference equation. All right, and the difference equation, the whole difference equation, including the x of n on the right side. Okay, so make sure that you understand how to do this. You can go back to the last slide and you'll see the difference equation. Difference equation had y to the n, so that becomes this, right? This is our y to the n. And then it was 2 times y to the n minus 1, so that's this term here. Notice we have the 2 out there, and n now is n minus 1. And then it was minus 8 times y of n minus 2, so here's the minus 8, and then this is the n minus 2. And then on the right side was our x of n, which we were told is equal to 3 times 1/2 to the n. Okay, so here is our difference equation with our particular solution plugged into it. So our goal here is to figure out what c is, all right? And again, this looks, like a horrible mess right now, but it's really not, because we can clean this up very easily. There's a couple of ways to do it. The easiest way is, again, just to let n equal 2 and see what happens here. This becomes 1/2 squared. This becomes 1/2 just to the 1, or just 1/2 by itself. And then 1/2 to the 2 minus 2, that's 1/2 to the 0, that's just a 1. So I factored out, notice all terms have a c, so I'm going to factor that out. And inside the brackets, we have 1/2 squared plus 2 times 1/2 minus 8. And that has to be equal to 3 times 1/2. Remember, n is equal to 2 here. All right. So now this is just, basic algebra. You can evaluate all of this stuff inside the bracket here, and then, you can evaluate this on the right side, and you just have to divide this by all the stuff in the square brackets. And if you do that correctly, you'll find out that c is equal to minus 1/9. So our particular solution, y sub p, is equal to minus 1/9 times 1/2 to the n. Finally, we can write our total solution. Our total solution, remember, is the sum of the particular solution and the homogeneous solution. So here is our homogeneous solution from the previous slide, these first two terms. And then this last term is our particular solution, which is shown right here. So this is the total solution to that difference equation. The next step is to find out what these two constants are here. And these are found using any initial conditions that are given. So suppose we were told that the system is initially at rest when n is equal to 0 and n is equal to minus 1. So if we plug in n equals 0, and then and this would be 0 on the left side. Plug in n equals 0, you'll get an equation with c1 and c2. You still can't solve for it though. But we have another initial condition. When we plug in n equals -1, This is also 0, and now we have to put a -1 up here in the exponent, and it'll give us another equation in C1 and C2. So we end up with 2 equations and 2 unknowns, which can obviously be solved. And so if you go ahead and do that algebra, you'll get C1 equals -2/9, and C2 is equal to 1/3. All right, so the final step then in this problem here is to represent the system by a block diagram. So in order to do this for a discrete time system, we need a subsystem or an element called a delay element. And a delay element is very straightforward in digital systems, for example. Delay elements are implemented by using a shift register. But we don't really need to worry about that right now. For all we need for our purposes, in this course at least, is a delay element is just a little box here with a D for delay, and all it does is it takes a signal coming in this case it's x of n. What comes out is x of n minus 1. It just delays this by 1. Okay, that's the purpose of a delay element. Very simple discrete time block diagram component. So let's go ahead and rewrite our difference equation with y of n all by itself on the left side, move everything else over to the right. So you can see that y of n, the output, is the sum of 3 terms. So let's start with the easy one. It's x of n. So I'm going to have x of n, my input, go into a sum, all right, an adder. The next, let's look at this term next. We have to add this also. So we have a -2, and I also have a y of n minus 1. So that's y, but it's been delayed by 1. So what I have to do is take my output y and bring it back and pass it through this delay element to give me y of n minus 1 coming out. I'm going to take that and multiply it by -2, right? This is the -2 right here, and put that signal into the adder. It's going to get added to the x here. But there's one more. There's this term too. So I need 8 times y of n minus 2. In other words, y is being delayed twice here. Well, we can use a little trick here. We've already got y of n minus 1 down here. We've already delayed it through this delay element. So let's just take that signal and throw it through another delay element here to get y of n minus 2 coming out. That multiplies by 8, all right, that's the coefficient there, and that in turn goes into the adder here. So notice this adder has 3 things going into it. It has the x, it has this term, and it has this term, all going into the adder, and what comes out is equal to y, because y is the sum of all those things. So this signal coming out of the adder is the output of our system. I'm going to show you one more example of solving a linear difference equation. This one is a bit more challenging for a couple reasons. It's a second order linear differential equation, but the problem here is that the roots are going to end up being complex. And so that will add a little bit of difficulty and complexity to this problem. So here's the linear difference equation that we're given. 2y of n minus 2y n minus 1 plus y of n minus 2 equals x of n. And x of n is just equal to a step function, u of n. All right, so here are all our steps. So we're going to start with the homogeneous linear difference equation. All we do is make the right side equal to 0, and we get this form right here. The next step is to find the characteristic equation. Remember what we do is we let y equal r to the n. So we get 2r to the n minus 2rn minus 1 plus r to the n minus 2. I'm just getting this right off of the linear difference equation, and that's equal to 0. And to solve this, we set n equal 2, because that's our lowest power exponent here. And when we set n equal 2, we get 2r squared minus 2r plus 1 equals 0. Now the problem here is you can't solve this by factoring. All right, in fact, so what you have to do is use the quadratic equation, But it turns out that the solution here are not real values of r, they're complex. So the two solutions for this characteristic equation are r1 is equal to 1/2 plus 1/2 j, and the other root is 1/2 minus 1/2 j. Notice these are complex conjugates of each other, as they always have to be. The next step here, we can finally, well, all right, we can write our homogeneous solution now. Y sub h is equal to, remember it's going to be C1, some constant, times the first root, this is R1 raised to the n, plus C2 times R2 raised to the n with the step function. And we attach the step function because the system is, we're told it's a causal system. Okay, the particular solution now, we've got our input function here is u to the n. So I'm going to let my particular solution equal just some constant times u to the n. Okay, and when I plug this back into the linear difference equation up here, I get this whole thing right here, and I can, clean this up by setting n equal 2. And when I do this, remember the step function is equal to 1 everywhere, as long as its argument is positive or 0. So I get 2a minus 2a plus a equals 1, and the solution of this is a is equal to 1. So it turns out my particular solution is just equal to the step function u of n. So the total solution to this difference equation is the sum of the homogeneous solution and the particular solution. So here it is written out here. We have solved for each of these up in the above steps. Now the two arbitrary constants C1 and C2 can be solved assuming we have two initial conditions. So if we assume that the system is initially at rest, y of n is equal to 0 for n less than 0. So for example, with n equals 0, I can plug that into the difference equation here. I'm sorry, plug it into, what we can do here is we can set n equals 0 in our difference equation up here. So I get 2 y of 0 minus 2 y of minus 1 plus y of minus 2 equals u of 0. But remember, these terms here have to be 0 because the system is at rest for any values of n less than 0. So this simplifies to 2 times y of 0 is equal to 1, or in other words, the initial condition y of 0, y at 0 is equal to 1/2. So y of 0 equals 1/2, and if we plug into our solution here, remember when n is 0, these terms in the parentheses just go to 1, all right, because anything raised to the 0 power is 1. So I end up with C1 plus C2 plus 1. And I can do the same thing for y of minus 1. I can kind of repeat this, this type of analysis here to get this equation here. So what results then is, from the initial conditions in the last step, is two equations in two unknowns. And so those are actually solved here. I won't go through the algebra there, but these are our two constants, C1 and C2, and notice they are also complex. So finally, I can plug these into the solution from, I believe it was step 6, the total solution, and this is what my solution looks like. So this form of the solution here is correct, but it's hard to really make any sense of this because this thing has all these imaginary number j's in it and so forth. And it turns out that we want a physical solution that has real numbers basically. And believe it or not, this thing is a real solution here. It just doesn't look like it in this form. So we have to do a little work here. So one thing we can do is these roots, R1 and R2, they're in rectangular form, A plus JB. We can convert them to polar form. Remember, polar form has a magnitude and a phase angle. So I won't, again, I'll spare you some of the details here, but we can use Pythagorean theorem to find the magnitude, and we can use also some trig here to find the phase angles, those are shown here. And so once we get that, we can plug those back in polar form, right? Now, it doesn't really look any better, but we're actually making some progress. We can simplify this by noting that if I pull out, I can factor out a minus 1/4, because that shows up several times here. And also I'm going to pull out this 1 over radical 2 to the n, which shows up in these two terms here. So that just kind of cleans things up. What's left is the addition of these two terms here. So one is 1 plus j times this exponential, and the other is 1 minus j times the exponential, but notice there's a minus sign up there. So if you look at these two terms carefully, you'll notice that they are complex conjugates of each other, because wherever there's a j here and a j there, it becomes minus j here and minus j there. So this, if we call this term here z, then this term here is z, complex conjugate of z, z star. All right, and there's a property about complex numbers that's very handy. If you have a complex number, any complex number, z, and you add to it its complex conjugate, you get 2 times the real part of z. So by using that property along with Euler's formula, we can convert this whole thing into sines and cosines. So, kind of amazingly, this form up here with all the j's in it boils down to our final result here, which is a real sequence. All right, there are no j's in this, no imaginary numbers, and it is a cosine function and a sine function. So these are oscillating, this is an oscillating signal. So this is kind of putting it all together. This was our linear difference equation that we started from up here. Here was our solution. This is the output of the system, which was, took quite a bit of effort to get on the last couple of slides. And by the way, this is a block diagram that I drew using this linear difference equation. All right, we learned how to do that earlier in this video. And so this is what the system would look like. And what this thing does, if you put a step function into this thing, it's going to spit out, this sequence here, which looks something like this. It's a decaying sinusoidal function, which is this part, superimposed on top of a step function. That's the one here out in front, which gets multiplied by the u of n. So this thing, the step function jumps up to 1 and goes straight across. And then on top of that, there's this decaying sinusoidal function, which you can see in the plot there. Okay, the last thing we're going to do here is, again, have you guys practice using what you learned. This problem activity, this system, this discrete time system, don't worry, it won't be anywhere near as complicated as the last example we just did. The roots won't be complex. They'll be real roots, so it'll be much easier to work through. What you're given here is this simple block diagram right here for a discrete time system, and you're asked to do to answer the following 6 questions here. So go ahead and pause the video and see if you can work out the answers to these, and we will discuss the answers next. Okay, so for the first part of the activity, you're asked to find the system's difference equation, and I gave you the hint here to label every arrow in the diagram, and that's absolutely essential to get it right. So what I'm going to do here is I'm going to start over here on the right side, and I've got y of n coming down here. So I'm going to label that y of n, multiply by 2, so this arrow here is 2 times y of n. That gets added to x of n, giving me x of n plus 2y of n coming out of the adder. That then goes through a delay right here. So I take this input here coming into the delay, and I simply delay it by 1. So x of n becomes x of n minus 1, 2y of n becomes 2y of n minus 1, and notice when I do that, I'm right back to the output, so all of this in red is equal to y of n. So I can write y of n equals x times n minus 1, x of n minus 1, plus 2y of n minus 1. And as is customary, I'm going to put my y's on the left. So I have y of n minus 2y of n minus 1 equals x of n minus 1. There is our linear difference equation that describes this system up here. Step number 2, find the homogeneous solution to the difference equation. So remember, the trick is to let y equal r to the n. So when I plug that into the difference equation, here's the difference equation again. Oh, and then we remember the right side we set to 0 because it's homogeneous solution here. So I have r to the n minus 2 r to the n minus 1 just by substituting this into here and here. And to solve this, I'm going to set n equal 1. I get that hint by looking at this exponent here. So when I set n equal 1, I get r minus 2 equals 0. Well, that's easy enough. R is equal to 2. So my homogeneous solution, y sub h, is equal to some constant c times 2 to the nth power. Step 3, find the particular solution for the input sequence x of n equals 1/3 to the n times the step function u of n. So from the table a couple slides back, my particular solution is going to have the same form as this with a constant. So it's going to be a times 1/3 of the n times the step function u of n. And I'm going to substitute that back into the difference equation, which is shown right here. When I substitute that back, oh, actually I showed it right here as well. When I substitute that in, I get this expression down here, all right, the whole thing. And in order to solve this and clean it up, I'm going to set n equal 1. And when I do that, and by the way, the reason I set n equal 1 is the lowest power of exponent is n minus 1. Here it is again, n minus 1. So by setting n equal 1, these are going to go to 0 on the top, right? And remember, anything raised to the 0 power is just 1. So I end up with 1/3 a minus 2a equals 1. To clean that up, I can multiply by 3 just to get rid of this fraction. I don't like that fraction. So a minus 6a is equal to 3, and therefore a is equal to negative 3/5. So our particular solution then is minus 3/5 times 1/3 to the n times u of n. Question 4, find the total solution assuming the system is initially at rest at n equals 0. Well, the total solution, remember, is just the sum of the homogeneous solution, y sub h, plus the particular solution, y sub p. So here those two solutions are added together. Now notice we haven't determined what this constant c is yet, but we can figure that out easily enough from the initial condition. So the total solution when n is 0 is equal to 0, because we're told that it's at rest at n equals 0. So this, when you set n equals 0 up here, you get c minus 3/5. Therefore, c equals 3/5, and we can now write the total solution to this linear difference equation is 3/5 times 2 to the n minus 3/5 times 1/3 to the n times u of n. Question number 5 says find the impulse response h of n. Remember the impulse response h of n, and we're going to find it by brute force. So the hint here was to solve the difference equation for y of n and determine y of n for n equal, we'll start with 0, and then 1, 2, 3, and so forth, using the fact that the system is causal and initially at rest. All right, so let's see how to do this. So the difference equation, remember, was this. Y of n equals 2y of n minus 1 plus x of n minus 1. So when we're dealing with the impulse response, we're going to let x, the input, be a delta function. So x of n is going to be delta of n. So we have x of n minus 1 here, that becomes delta of n minus 1. Now the output of a system, when the input is a delta function, is h, which is the impulse response. So in other words, I'm going to let y of n equal the impulse response h of n. So this y of n just becomes h of n. This term here, we just replace y with h. So here's our equation to figure out what h of n is. All right, and we're going to do this, brute force. Basically, we're going to do this recursively. We're going to start with n equals 0, and we're just going to plug in 0 for n. and we get h of 0 equals 2h of negative 1 plus delta of minus 1. Now, what do we know about this system? Well, we're told that it's causal and initially at rest. So that means h of minus 1, that's the impulse response when n is less than 0, has to be 0. So this first term is a 0. We also know the delta function at minus 1 is also a 0. So our initial h value, h of 0, is just equal to 0. All right? Let's go now to n equal 1. Well, when n equals 1, h of 1, again, what I'm doing now is I'm plugging n equal 1 into all these three terms here in our equation. So I have h of 1 equals 2h of 0 plus delta function of 0. Now, 2h of 0, remember h of 0, this is where we're using recursion. We already found that h of 0 is equal to 0. So this is a 0 here, and the delta function at 0 is a 1. So now we've got an output. The impulse response when n is equal to 1 is equal to 1. And we just keep going through this. We do this for n equal 2, and we'll find out that we get 2. When n is equal to 3, we get 4, and so on and so forth. Okay, and we can keep going like this. Finally, when we get to n equal 4, notice I just had to make some corrections here. I had some typos. The value of h at n equal 4 is equal to 8. So our output goes 0, 1, 2, 4, 8, and then each time it would keep multiplying by 2. So we can put this into a closed form. The impulse response h of n, there's two ways to express it. You can say it's 2 to the n minus 1 times a step function of u of n minus 1, or you could say it's equal to 1/2 times 2 to the n of u of n minus 1. And you get that just by looking at how it's growing here. The last question was, is the system stable? And obviously, this thing, if it keeps doubling every tick of the clock here, it's going to grow without bounds. So no, this system is not stable. So before we finish up this chapter, just some final thoughts here, kind of looking ahead. One of the things we did in this chapter 2 was we learned that without any knowledge of what's inside a system, they sometimes call this a black box, where it's sort of a mystery here, we can predict how the system will respond to any input just by measuring a system's impulse response. So remember, if we put an impulse, delta t, into this system, it's going to spit out an output which we call the impulse response. And if we know the impulse response, then we can figure out what this system will do for any input just by taking, remember, the convolution of the input with the impulse response. So the output of a system is equal to x convolution with h. Now, one question comes up. Can we figure out what's inside of this box? In fact, in this case right here, if we just look at the impulse response of the system, can we sort of go backwards and figure out what's inside the box just by looking at the form of this impulse response? And the answer is yes. However, we're going to have to develop some powerful analysis tools first. And this will be the subject of the upcoming chapters. So that is it for chapter 2. It was a kind of a long and somewhat complicated chapter. We had convolution, we had differential equations, and we had difference equations. So there was quite a bit of material here and a couple of long lectures here to finish up the chapter. But we're going to sort of switch gears now in the course and move on to some different types of topics next. I'll see you shortly in chapter 3. Goodbye.